Jake Gardiner takes a penalty shot. A save. A post. And a beautiful move. Sure, get the goalie angry when it's my turn.
I'd recommend deking.
Here goes. Gardner realizes I need a trick.
Carry the puck in your hand, put this in the net.
The old second puck trick.
One more, Jonas. The only way I could score on you. Carry a puck.
For the Edmonton Oilers, the penalty shot is serious business.
So we looked at every shootout for the last 5 years.
The team president is listening to a statistical study about it. Around the table with him is the analytics group. A developer of software, a professor of computer science, a director of research and analysis, a blogger, a committee trying to find meaningful patterns in raw data.
Quite frankly, I don't have enough hours in the day to be, experimenting with stuff that we didn't think would hopefully be beneficial.
The hot hand effect.
The committee is reporting on something called the hot hand. If a player scores in a game, does the data show he's more likely to score in the shootout?
Why wouldn't we try to tap into that source and see if there are any answers there for us?
You are 0.8% more likely to score if you score the one goal, which is within your statistical limits, meaning that there is no effect.
So there was no variance whatsoever?
No variance whatsoever. No.
And
Analytics for me is to ask questions to get answers to things we hadn't thought about before.
left shooters on right goalies and right shooters on left goalies. Did you look at that?
How else can you get better? And that's just gathering information and hoping to gain that little extra 2% that perhaps other teams aren't doing.
Some say the future of sports is in this kind of data mining. Here's another good example.
It's late in the game. We're down by a goal. I'm looking to the bench to see if the coach wants to pull me and put on an extra attacker.
If I pull him and we score, I'm a hero. If I pull him and they score, I'm the lead story on TSN. What should I do?
Most NHL teams follow tradition or a gut feeling. Roughly, it's something like this.
I'm going in and the goalie's coming out if we're down a goal with a minute to go. If we're down by 2, I'm going in earlier. But I don't have to use my gut anymore. I've got an in-depth statistical model I can follow. It was developed by David Beaudoin at Laval and Tim Swartz at Simon Fraser. Here's what they found.
My team's on the road. We're down a goal with 3 minutes to play. Pull the goalie.
We're down by 2 at home with 6 minutes to go. Pull the goalie. If we score pretty quickly, the model says, put the goalie back in. But if we're still behind with 3 minutes to go, pull the goalie. Even if I'm in the penalty box and we're shorthanded with 2 minutes to go, pull the goalie.
The statistical analysis was even able to quantify some pretty crazy situations.
We're on the road, 3 goals down, with 12 minutes to go.
But you got a 5-on-3 power play for nearly 2 minutes. Am I repeating myself? Pull the goalie. Pulling the goalie more effectively might only make the difference of a point or a point and a half in a season, but that could be the difference between the playoffs and golf.
Our top story tonight, controversial head coach Jay Ingram was at it again last night. He pulled his goalie with 12 minutes to go. He played the odds and lost.
That is the Golden Gate Bridge. Just across the bay is the University of California, Berkeley. That's where you'll find one of America's top chemists, Dr. Gabor Samorjai. He has discovered what makes ice slippery. He used this laser setup.
Some frequency generation vibrational spectroscopy. This is a jargon of the field. It's called nonlinear laser spectroscopy.
It saw the surface at a molecular level. And he also used this technique.
Low-energy electron diffraction.
He bounces electrons off the surface.
That is called diffraction. In a diffraction, you don't lose energy, but you change the direction of scattering of the electrons.
Each element scatters in a unique way. So what did these sophisticated techniques discover about the surface of ice?
To answer that in a single sentence, there is a layer of water on top of ice, which makes it slippery.
And that layer exists down to minus 183 degrees Celsius. The thickness of the layer varies, but it's always measured in mere molecules.
The molecular layers, depending on the temperature, one molecular layer at very low temperature to 30, 40 layers of water as you go to higher temperatures.
And now, for the first time, there's stunning video of the ice surface. Those black and white circles are drops of liquid sitting on ice. You're seeing something smaller than a billionth of a meter. Here's what happens when the temperature gets warmer. Here, it's getting colder.
These droplets had no detectable crystal faces.
In other words, they remained as water and would as long as there was a surface. Here's a fun demonstration.
You put ice cubes together. By putting it together, you eliminate the surface in between. If there is no surface, there is no water layer. In 1850, Faraday showed that once you eliminate the surface, the ice refreezes where there was water.
This single cube has a lot of surface.
There is a lot of water here.
And the stacked cubes?
As soon as you eliminate the surface, it freezes. Isn't that cute? And you go, and they stuck together. Canada should like that, because they live with this stuff.
Just how slippery is ice? This will give you some idea. I'm here in front of the home of the Toronto Maple Leafs. Let's say I launch a terrifically fast slap shot, something like 160 kilometers an hour. I know, but no boards, no wind, just beautifully smooth ice as far as the eye can see. Just how far would that puck go?
It speeds up Bay Street. Friction starts slowing it down.
There's a little bit of friction from the ice, but actually most of the friction comes from the air.
But fighting that friction is the speed of my shot.
When the puck is shot at speeds above 50 miles per hour, there's a lot of turbulence around the puck, and that contributes to lowering the drag.
Eventually, friction will win. Total distance traveled?
It's about 2 kilometers.
The puck stops here.